Brace yourself for a mind-bending journey into the unknown. Get ready to explore the top 14 secrets that make the quantum world a playground for philosophical contemplation. Are you prepared to question everything you thought you knew? Let's dive in. Our quantum adventure begins with secret number 14. Quantum entanglement. Imagine two particles doing a dance, connected in a way that's like magic. This is the incredible dance of quantum entanglement. At the center of entanglement is something amazing, the idea that changes in one particle instantly affect the other no matter how far apart they are. Let's dive into what makes entanglement so fascinating in simple terms. First, we have instant connection. Changes in one particle happen right away in the other, breaking the rules of distance that we are used to. Next up is non-locality. Even if the particles are far apart, they stay connected, like having a secret language that travels through space and time. But how do particles get tangled up in the first place? Let's talk about the cool process of making entangled pairs, like creating a magical bond between them. Think of a single photon splitting into two. These two photons are now connected and their destinies are linked. Now, let's look at a fun example. Two photons that are entangled. When we measure one photon, the other's properties are instantly known, no matter how far apart they are. This mind-blowing idea led to a big debate called the EPR paradox, challenging what we thought we knew about quantum stuff. Now, let's see how this magical connection can be used in the real world. In quantum communication, entanglement is like a superhero. It helps with things like quantum teleportation and making sure that our secrets stay safe with quantum key distribution. And in the awesome world of quantum computers, entanglement makes them super powerful. It's like having special language between qubits, making them work together in ways that regular computers can't. But wait, there are still some puzzles and debates. Scientists are figuring out how information travels and what non-locality really means. Experiments like Bell's theorem shows that entanglement is a real thing, pushing our understanding of how the quantum world works. What philosophical questions does the idea of entanglement spark in your mind? Share your philosophical gems in the comments. I am eager to explore your perspectives. Secret number 13. Wave-particle duality. In this secret, we explore the duality of particles. They act as both waves and particles, challenging our classical intuition. The wave-particle dance lies in the heart of quantum mechanics. Imagine particles, like electrons and photons, switching between, acting like waves and particles, creating a puzzle that challenges everything we thought we knew about matter and energy. Let's uncover the important things that make wave-particle duality so cool in simple terms. First, particles show off their wave-like moves when no one is watching. They make interference patterns and diffract, which are fancy ways of saying they act like waves. But when we look at them or measure them, they behave like normal particles. They stay in one place and show their solid side like the tiny bits of stuff we are used to. To understand this quantum dance, we use something called wave function, a maths thing that tells us how a particle behaves. The square of this function gives us the chances of finding a particle in a certain state. Now let's talk about famous double-slit experiment. When particles, like electrons or photons, go through two slits, they create a pattern on a screen behind them. It's like they are dancing. But if you peek at them, they stop dancing and act like normal particles. This experiment challenges the idea that particles are just tiny solid things. Enter Niels Bohr's idea of complementarity, a fancy way of saying that particles can be both waves and particles. But we can see only one side at the time. So how does this dance of particles and waves help us in the real world? Let's talk about applications. In electron microscopes, where we explore tiny things, understanding electrons as both particles and waves helps us see details we couldn't see before. And the maths we use in quantum mechanics, like the Schrödinger equation, relies on these wave-like behaviors. As we navigate this quantum dance, there are challenges and different ideas. Some say particles are in many states at once until we look and then they pick one. Others say all possible outcomes happen in separate parts of the universe at the same time. It's like a big mystery we're still figuring out. Our wave-particle duality is tied to the history of quantum discoveries. Louis de Broglie and experiments by Davison and Germer laid the foundation for this mind-bending concept. Secret number 12. Quantum superposition. Imagine particles existing in multiple states simultaneously. That's the magic of quantum superposition. It's a concept that opens the doors to a realm of possibilities. Picture this particle doing a quantum dance, breaking the rules of regular physics, and hanging out in multiple states all at once. Sounds crazy, right? Well, that's the magic of quantum superposition. Tiny stuff like electrons and atoms have a special talent. They can exist in different ways at the same time. Let's find out how this quantum magic works. Now, how does it actually happen? Welcome to the land of probability amplitudes, where the chance of finding particle in a certain state gets expressed in a super cool way. Through superposition. Superposition's secret weapon is the combo move called linear combination. It's like particles cruising through a chance-filled adventure until we decide to take a peek. Hold on tight as we dive into a famous story, Schrödinger's cat. In a hidden box, a cat's fate just tangled with the radioactive atom. It's both alive and not alive at the same time until someone opens the box. Now, let's see how this mind-bending concept steps into the real world. Say hello to quantum computers. Quantum computers love superposition. They use it to be superheroes in the computing world, trying out many answers at once. It's like doing a bunch of maths tricks super fast. But as we dig deeper, we hit some roadblocks and start thinking about mysteries of quantum land. How does superposition decide on a state when we look? This is the measurement problem. And here comes the wild idea. Many worlds interpretation. It says all the different outcomes live in separate universes, keeping the superposition magic alive in different realities. Before we move on, what's your take on the implications of quantum superposition for our perception of the world? Drop your thoughts in the comments below and let's build this quantum philosophy discussion. Secret number 11. Quantum tunneling. Breaking through classical barriers, this secret introduces us to quantum tunneling. Particle journeys that defy classical physics, tunneling through energy barriers and unveiling the extraordinary possibilities at the quantum level. Think about particles having this incredible superpower to go through barriers that regular physics says are impossible. That's the mind-blowing world of quantum tunneling. Let's uncover why quantum tunneling is so cool in simple terms. Firstly, quantum tunneling is about probability. It's like a chance of a particle ending up on the other side of barrier even if it doesn't have enough energy according to normal physics. Imagine a particle facing a wall it can't jump over. In regular physics, it's stuck. But in the quantum world, there is a chance, a small one, that it can sneak through the wall. To understand tunneling, we have to talk about quantum mechanics. It's the way particles act like waves that makes tunneling possible. Particles are like wavy things, and their wavy part stretches into places normal physics say no-go. That's where tunneling becomes a possibility. Let's look at a space example where tunneling takes the spotlight. Nuclear fusion in stars. In stars, protons face a big energy barrier. Regular physics says it shouldn't happen. But thanks to tunneling, some protons break through, making the nuclear fusion that's light up stars possible. Now, let's see how this super cool phenomenon shows up in our tech world. The applications of quantum tunneling. In tiny tech, there's something called scanning tunneling microscope (STM). It uses tunneling to create super detailed pictures of really tiny things like atoms. And in electronics, tunnel diodes and tunnel field effect transistors use tunneling, making super advanced electronic devices. But hold on. There are challenges to this quantum coolness. Tunneling happens super fast, making it tricky to watch directly. And the idea of particles borrowing energy to jump barriers adds an extra layer of mystery. To really get into tunneling, we need to talk about math's magic of quantum mechanics. The Schrödinger equation is like the superhero that tells us the chance of this amazing journey happening. Secret number 10. Quantum teleportation. Not the science fiction teleportation of people, but the ethereal transfer of quantum states. The cosmic dance of entangled particles holds the key to this mesmerizing phenomenon. So forget about teleporting entire beings. We're talking about zapping quantum info across space. And our star for today is quantum entanglement, the secret sauce that makes it all possible. Let's get into why quantum teleportation is like a cosmic dance. First of all, it's all about quantum entanglement. When two particles are entangled, they're like besties with synchronized moves no matter how far apart they are. It's like magic, but it's a science. But here's the kicker. We also need some classic communication to spill the beans about what's happening with our entangled pals. Now, let's break down the cosmic ballet in simple steps where quantum teleportation unfolds like a superhero rescue mission. Step number 1. Entanglement creation. Two particles becoming quantum besties, setting up the cosmic magic. Step number 2. Quantum measurement. A tricky measurement happens on both the particle to be teleported and its entangled buddy. Step number 3. Classic communication. A cosmic message sent through regular channels spills the beans about a quantum state. Step number 4. State reconstruction. At the other end, the quantum state is brought back to life using the secrets shared through classic means. To understand the fancy moves in this quantum show, we peek into the math side of things. Teleportation is like a dance of entanglement, superposition, and artful moves of quantum measurement. Imagine you have two particle buddies, A and B, doing the entanglement tango. Now, you want to teleport the quantum state of another particle, C, to the other side of the universe. It's like a superhero rescue, a dance of measurements, classic communication, and bringing quantum states back to life. How does this cosmic dance play out in the real world? Quantum teleportation is like a rock star in quantum communication and computing. In quantum communication, it helps send super-secret quantum messages across huge distances. And in quantum computing, it's like the backstage pass, allowing quantum states to jump between qubits like magic. But wait, this cosmic dance isn't without its challenges. Creating entangled particles and pulling off super-precise quantum measurements are like doing cartwheels in space. Not that easy. And here's the kicker. Quantum teleportation doesn't mean sending stuff like in sci-fi. It's all about sending the quantum info, not the actual matter. Secret number 9. Quantum uncertainty. Imagine a world where particles dance to their own mysterious tunes, defying our classical understanding. That's the enchanting world of quantum uncertainty. So, what makes quantum uncertainty such a mind-boggler? Let's unwrap the key aspects that challenge our classical intuition. First off, we have the Heisenberg uncertainty principle, revealing a fascinating connection between a particle's position and momentum. The more precisely you measure one, the less you can know about the other. It's like a quantum dance of precision and limitation. Let's bring in the maths. The Heisenberg uncertainty principle is mathematically expressed as delta x times delta p is greater than or equal h bar divided by 2. Break it down and you'll see how the uncertainty in position, delta x, and momentum, delta p, are intertwined, thanks to the Planck constant h bar. To make sense of this, picture an electron. The more accurately you pinpoint its location, the fuzzier its momentum becomes. Why? It's the wave-particle duality in action, revealing the quantum nature of particles. Now, let's dive into the implications. Heisenberg's uncertainty principle challenges the classical dream of pinpoint precision. It introduces an element of inherent randomness into the fabric of quantum systems, shaking up our notions of determinism. Hold on. Uncertainty doesn't stop there. It also extends its reach to other pairs of conjugate variables like energy and time. The more you know about one, the less you can determine about the other. How does this uncertainty dance affect the quantum landscape practically? It's not just theory. It has real-world applications. Quantum mechanics calculations and quantum cryptography are just a few areas where this uncertainty plays a pivotal role. As we waltz through this quantum dance, challenges and debates emerge. The idea of particles borrowing energy and the incredibly short tunneling times add layers of complexity to our understanding. To get to the heart of uncertainty, we delve into the elegant mathematics of quantum mechanics. The Schrödinger equation is our guide, elegantly capturing the probability of this enthralling dance. Before we move further, I've got a question for you. How does uncertainty resonate with your thoughts on reality? Share your philosophical answers in the comments. Secret number 8. Quantum interference. Particles, like musicians in an orchestra, creates patterns of harmony and cancellation. Quantum interference is the choreography behind some of the most astonishing quantum phenomena. In the quantum zone, things get groovy. Particles aren't just hanging out, they are surfing waves. Quantum interference kicks in when these waves come together or drift apart, creating some trippy patterns. Our journey starts with the superposition principle. Imagine particles, like electrons, doing a fancy dance, being in multiple states at the same time. As these particles move around, their wave dances mix up, creating quantum interference. Patterns that are like a light show of highs and lows. Now imagine a classic experiment. The double-slit experiment. Particles waltz through two slits, creating a stage of patterns. When the wave crests meet, it's a party called constructive interference, making things intense. But when the crest meets trough, it's a chill zone called destructive interference, making quiet spots. But hold on, the fun doesn't stop in the lab. Quantum interference has real-world jobs. In quantum computers, it's like a fancy algorithm dance where qubits make sure the right moves happen through constructive interference. In secret quantum chats, quantum interference takes the lead in quantum key distribution, ensuring that messages are safe. Let's meet the quantum superhero Mach-Zehnder interferometer. It's like a conductor with mirrors and beam splitters, making sure that quantum interference hits all the right notes. This quantum maestro plays a role in quantum info and communication, making sure our data transmissions are like a secure music score. But like any dance, quantum interference has its challenges. External noise can mess up the groove, and quantum decoherence tries to crash the party. Even with challenges, quantum interference has gigs in quantum sensing, making super accurate measurements. Looking ahead, scientists are working on perfecting the interference dance, keeping the quantum symphony going. There's a whole universe of possibilities waiting to be explored. We are halfway through this mind-bending journey into the secrets of quantum realms. If you're enjoying trips so far and want more mind-expanding content to philosophize, make sure to subscribe to our channel. Subscribing not only unlocks a universe of quantum knowledge for you, but also helps us continue creating more fascinating content. Join our community, and together let's continue to expand our minds. If you've just subscribed to our channel, let us know you're part of the journey. Drop a comment saying I'm in. We look forward to sharing more mind-bending content with you. Now, let's get back to unraveling the secrets of the quantum world. Secret number 7. The quantum measurement problem. A philosophical puzzle that challenges our understanding of observation and reality in the quantum realm. In the quantum realm, things get a bit tricky when we try to measure them. Imagine this. Particles in multiple places at once, doing a sort of cosmic dance. But here's the twist: the moment we measure them, they snap into a definite state. Now, this is where quantum measurement problem waltzes in. It asks simple, yet mind-boggling question. What exactly happens when we measure a quantum system? The answer, my friends, is not as straightforward as it seems. According to the laws of quantum mechanics, particles exist in a fuzzy, probabilistic state until someone or something observes or measures them. But here's the kicker. The act of measurement seems to force them into a specific state, abandoning their dance of possibilities. Enter Schrödinger's cat, a thought experiment that illustrates the measurement problem. Imagine a cat in the box with quantum trigger that might release poison. According to quantum principles, the cat is in the superposition of alive and dead until someone opens the box to check. This challenges our common sense of understanding. Is the cat both alive and dead until we look? Or does the act of observation create the reality? Let me know what you think. Share your philosophical ponderings in the comments below and let's unravel this mystery together. Scientists and physicists have proposed various interpretations and solutions to this mind-bending enigma. Some suggests parallel universes branching off with every possible outcome, while others argue for a deeper understanding of the nature of measurement in quantum mechanics. Quantum entanglement adds another layer to the mystery. When particles become entangled, the measurement of one instantaneously influences the state of the other regardless of the distance between them. The quantum measurement problem remains a hot topic of debate, sparking discussions about the nature of reality, the role of consciousness, and the very foundations of quantum mechanics. Secret number 6. Quantum decoherence. It's the process that threatens to turn the symphony into chaos. Understanding decoherence is crucial for harnessing quantum power. Imagine a particle's doing a fancy dance, existing in multiple states at once. This is coherence, a big deal in quantum world. But hold on, here comes the game changer. Quantum decoherence. It's like an unwelcome guest disrupting the quantum party. Decoherence happens when our quantum system gets tangled up with the outside world. Picture a dance where the quantum system and its surroundings start to tango, leading to a complicated and messy dance floor. As this dance gets wilder, the once smooth moves of superposition start falling apart. The quantum symphony turns into a bit of chaos. Quantum interference, which makes quantum systems special, starts fading away, and classical-like behavior takes over. Decoherence draws the line between cool quantum stuff and the more predictable classical behavior. Now, let's talk consequences. First up, the quantum advantage takes a hit. Decoherence messes with quantum info processing, making it less superpowered. But hey, the story doesn't end here. Scientists are on a mission to tackle this challenge and keep our quantum states safe. Meet the heroes: quantum error correction and quantum error avoidance. They're like the shields protecting our quantum computations from the effects of decoherence. In the quantum computer realm, where keeping qubits happy is crucial, fighting decoherence is a top priority. The clock is ticking, with the decoherence time setting the beat. Researchers are working hard to stretch this time, minimize outside interference, and develop strategies to fix errors. Why does all this matter? Because the future of quantum tech depends on it. Quantum computers and quantum communication, these awesome innovations rely on keeping things coherent. Understanding and handling decoherence isn't just science, it's the key to unlocking full power of quantum technologies. Secret number 5. Quantum computing. In this quantum secret, we're not dealing with regular zeros and ones. Nope, we've got qubits. These cool quantum bits that can be 0, 1, or both at the same time. Let's check out why quantum computing is like the superhero of computing world. Quantum computing has some special things that make it stand out. First, there's superposition. It's like qubits doing a multitasking dance, being in many states at once. Next, we've got entanglement. A quantum connection where qubits can be besties, no matter how far apart they are. And then there's a quantum parallelism, where qubits team up to solve the problem super fast, checking out lots of solutions at once. So how do qubits do their magic? That's where quantum gates come in. They're like the superhero moves of quantum algorithms, not like the regular logic gates you find in your everyday computer. Quantum algorithms are like the special tricks that quantum computers can do. Shor's algorithm, for example, can crack codes way faster than regular computers. Quantum supremacy is the big goal. It's when the quantum computer beats even the mightiest regular computers. Imagine a whole new level of computing power. Where does all this quantum awesomeness lead? Quantum computers can do some mind-blowing stuff. In the computer security world, quantum computers challenge our usual ways of keeping info safe. They're like superheroes in logistics, finance, and science, solving problems at lightning speed. Plus, they might revolutionize how we discover new drugs. But hold on. Our quantum journey isn't all smooth sailing. Quantum computers are a bit sensitive and can make mistakes. Scientists are working hard to fix these issues and keep quantum computers stable. Big practical quantum computers are still in the making, but with all the smart folks working on it, we're getting closer to a new era of superpowered computing. As we're getting closer to the pinnacle of our journey, we're about to explore. Secret number 4. Quantum Zeno effect. Picture a quantum system trying to change or transition between states. According to the quantum Zeno effect, if you observe it frequently enough, it remains frozen in its current state, almost as if time has hit a pause button. Think of it as wielding a quantum stopwatch. Each observation resets the clock, preventing the system from completing its natural progression. It's like catching a fleeting moment and holding it in quantum snapshot. Now, you might be wondering, why does this matter? Well, scientists has explored quantum Zeno effect in various fields, from quantum computing to understanding the dynamics of particles. It's not just a curious quirk, it has real-world applications. Here's a fun way to wrap your head around it. Imagine you're flipping a quantum coin, a particle in superposition of heads and tails. If you keep checking its state quickly, the quantum Zeno effect might keep it in that superposition, making it a quantum coin forever in the air. However, like any quantum tale, there are limitations and oddities. The quantum Zeno effect works best under specific conditions, and its interaction with other quantum principles adds layers of complexity to our quantum understanding. So, what's your take on quantum Zeno effect? Is it a glimpse into the relationship between observation and reality, or just a quirk in the quantum world? Share your thoughts in the comments below. Secret number 3. Wheeler's delayed choice experiment. Imagine a cosmic scenario where a choice made in the present seems to influence events that happened in the past. Sounds like science fiction? Welcome to Wheeler's delayed choice experiment, where the quantum realm serves up a plate of the paradox. In Wheeler's experiment, a photon faces a crossroads with its fate determined by a choice made after it has already traveled. It's like sending a traveler on a journey and deciding the path they took after they've arrived at their destination. Here's the kicker. Whether the photon behaves like a wave or particle depends on a decision made after it has passed through the crossroads. It's as if the present choice reaches back in time and affects the photon's past. This experiment taps into the magic of quantum superposition. Before the choice is made, the photon exists in multiple states simultaneously. A quantum dance that keeps us on our toes. Now, imagine the implications. The choice made in the present seems to retroactively determine whether the photon experienced interference patterns as a wave or acted like a particle with a definite trajectory. Wheeler's delayed choice experiment isn't just a scientific puzzle. It's a philosophical journey into the nature of reality. It asks us to reconsider our understanding of time, causality, and the role of observation in shaping the quantum world. Believe it or not, these quantum head-scratchers have a real-world applications. Understanding the delicate dance between choice and consequence in quantum realm could impact technologies like quantum computing and communication. Now, what's your take on Wheeler's delayed choice experiment? Does it make you question the flow of time and causality in the quantum world? Share your thoughts in the comments below. Secret number 2. Quantum consciousness hypothesis. Imagine a dance inside our brains. Could tiny structures called microtubules be the stage for quantum processes? Picture the small dancers, the microtubules, performing a delicate dance of different possibilities. Now let's talk about orchestrated objective reduction theory by Roger Penrose and Stuart Hameroff. According to this theory, quantum processes within microtubules collapse to specific states, influencing how neurons dance in our brains. But there are challenges to this quantum dance. The warm and noisy brain environment makes it tricky to keep quantum effects intact. Plus, we're still figuring out how much quantum effects really influence our thoughts. In science, there are other ideas too. Some suggest that bigger, classical processes might be the conductors of our thoughts. Think of it like a big dance guiding our consciousness. The quantum consciousness hypothesis makes us think deeply. It raises big questions about how the dance of tiny particles connects with our thoughts and feelings. As scientists keep exploring, experiments carefully check if quantum processes play a role in the biology of our brains. It's like solving a mystery while being really careful about the clues. But the quantum consciousness hypothesis is still a big mystery. Some scientists love the idea, while others aren't so sure. It's like a big puzzle we're all trying to solve. Before we unveil the climax, let me ask you, do you believe quantum processes could influence consciousness, or do you think classical processes in the brain are the primary conductors of our conscious experiences? Share your philosophical musings in the comments below. We can't wait to explore the depths of your thoughts. Finally, our last secret. Secret number 1, the pinnacle of our exploration. The observer effect. This secret not only delves into the role of consciousness in quantum reality, but sparks a cosmic symphony of philosophical questions. Picture this. In the quantum world, the act of observation isn't just a passive gaze, it's an active participant influencing the behavior of particles. In the quantum dance, particles exist in the state of probabilities until observed. It's like they're playing hide and seek with their properties, revealing themselves only when someone is watching. Enter the Heisenberg uncertainty principle, a quantum rule stating that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Here's the twist. The act of measuring one property alters the other, and the observer becomes an integral part of this delicate quantum equation. Let's unravel the mystery with the iconic double-slit experiment. When particles aren't observed, they behave like waves, creating an interference pattern. But the moment we observe, they pick a definite path, behaving like particles. Now, some ponder, does consciousness play a role in this quantum tango? It's a tantalizing question that sparks debates and philosophical musings. Beyond the theoretical, the observer effect has practical implications. In quantum technologies, understanding and harnessing this effect is crucial for developments like quantum computing and communication. Now, here's the twist. The observer effect raises profound questions about the role of consciousness in shaping reality. Does the act of observation create the reality we see, or does it merely reveal what was already there? Here's the grand question for you. How does the observer effect influence your philosophical understanding of consciousness and reality? Share your cosmic reflections in the comments, and let's elevate this discussion. That concludes our philosophical odyssey through the top 14 secrets of quantum reality. Thank you for joining us on this cosmic journey. If you enjoyed philosophizing with us and haven't liked or subscribed yet, now's the perfect time. Go ahead, hit subscribe, like, and don't forget to share your quantum musings in the comments. Until next time.